7th, 2021. Welcome to the Undergraduate Research Symposium. This presentation is called Data-Driven Crystal Ball. And we will first hear from Ben Backen, who is going to talk with us about predicting stock market fluctuations based on Reddit data. So I'll turn it over to Ben, and please, we'll have the Q&A at the end, but feel free to put any questions in the Q&A while you are listening to our presenters. Thanks.
Great, thank you. Start sharing my screen. All right, does that look okay?
Yes, that looks great. Go ahead.
Cool. All right, 2 months ago, a group of Reddit users caused GameStop short sellers to lose nearly $13 billion, bankrupting at least one hedge fund. I wanted to find out if we could abstractly use the collective knowledge and decision-making of casual daytime traders to predict stock market fluctuations. Before we get started, I want to thank Sam Schwartz for being my mentor through this project. He's been really supportive and I've learned a ton. I also want to thank the University of Oregon for letting me flood their SQL server with Reddit posts. My research question is, how well can we predict if a stock's price is going to increase or decrease based on Reddit posts? Let's start by defining the scope of this experiment. I limited the posts that I considered to only those from a particular section of Reddit called Wall Street Bets. This is where the GameStop activity originated. I also focused just on GameStop stock because this had the most activity and media coverage. Finally, I restricted the time frame to be between January 1st and February 21st, as this was the peak of the GameStop trading. To answer my research question, I used a neural network. The output is the high and low prices on a particular day for GameStop stock. And in case you don't gamble on the stock market, the high and low refer to the highest and lowest prices that the stock hits as the price moves up and down throughout the day. Then the corresponding input is all of the Reddit posts mentioning GameStop in the 4 days preceding our prediction day. More specifically, the Reddit posts, or the Reddit features rather, that I consider are the number of upvotes on a post. This gives some idea of how much the post has been seen. The ratio of upvotes to downvotes, which could approximate how positively people feel about the post. The number of awards given to the post. Giving an award costs real money, so it may also indicate positive feelings. And the number of comments on the post, which shows how much interaction there is. The neural network knows absolutely nothing about the stock's price or price history before it makes a prediction. It only sees 4 prior days of Reddit posts. The first task is extracting the input data from Reddit. Unfortunately, Reddit doesn't make it easy to scrape their website. While they do have an open API that lets you grab specific posts, you can't use it to collect swaths of data between specific times. Luckily, there's another API called PushShift, which lets you do exactly that. Except PushShift's archive isn't updated, so almost all the posts are collected and stored with 0 upvotes, 0 awards, 0 comments, etc. I solved this problem by using PushShift to collect the links for over 750,000 Wall Street Bets posts that mention GameStop, and then using the Reddit API to update the posts data one by one. Collecting the stock price data is straightforward. I use the Yahoo Finance API to grab the highs and lows for GameStop. I then store the posts and the stock prices in a MySQL database. Now that I have all the data in one place, I need to figure out how to articulate this information to the neural network. The input is a 3-dimensional tensor. On the inside, going across here, we have the Reddit vectors, whose entries are the number of upvotes, the upvote ratio, the number of comments, and the number of awards. Then each of these matrices holds the Reddit vectors from the 4 days preceding our prediction day. And there are around 70,000 vectors in each matrix. Finally, our tensor holds 51 of these matrices, each pointing to one of the days between January 1st and February 21st. The features that we're considering are on drastically different scales. For example, a post might have 10,000 comments and 10 awards, but that doesn't mean that a comment is 1,000 times more significant than an award. To resolve this and help the neural net learn more quickly, all of the features are standardized with 0 as the mean. Our input also needs to be rectangular, meaning that all of the matrices within our tensor have the same shape. Since different days have different numbers of posts, the day matrices need to be imputed. I decided to fill the gaps with 0 vectors, which represent average posts, since the data is standardized. The output has a very similar shape to the input. Here we have a stock vector storing GameStop's high and low price for a particular day. This vector is then duplicated around 70,000 times so that each GameStop vector aligns with one of the Reddit vectors. So now we have our training data. Our input is a tensor with 51 matrices of Reddit data, and our output is a tensor with 51 matrices of stock data. Finally, we're ready to construct the neural network. The neural network is built with an input layer that has around 70,000 perceptrons, one for each Reddit vector in one of the matrices. There are then 2 hidden layers with 1,024 and 32 perceptrons respectively. These first 3 layers use ReLU for their activation function, and then these converge on 2 output nodes. One represents the high price and the other represents the low price for the day. It's important to note that these outputs are still standardized, so to get actual dollar amounts, we have to invert the standardization process. I found that the loss functions plateaued after around 300 iterations, so I let the models train for 300 epochs. To assess the accuracy of this model with novel data, I used Monte Carlo cross-validation. The program randomly partitions the training data into 2 sets. 80% of the data remains in the training set, while 20% is separated and remains unseen by the model. After the neural network trains on this data, it then makes predictions on the validation data, so the 20%. I record the predictions alongside the true stock prices for that day so that we can compare them later. This process is repeated 10 times. With this validation data collected, we can analyze how well we did. Here we have 2 scatter plots that show us the accuracy of the model when predicting highs and when predicting lows. Along the x-axis are various days that the model did not see when it trained. Then on the y-axis, each day is marked by the direction that the price changed. If the value is 1, then the high increased for that day. If the value is -1, then the high decreased that day, and similarly for the lows. The purple points are days that the model correctly predicted an increase or a decrease, and the red points are incorrect predictions, and they show the true direction for that day. To get this data, I took the discretized derivatives of both the predicted values and the true values just by subtracting the prices on consecutive days. That gives the slopes of change in price, and then I look at the sign of those slopes, positive or negative, to see if the price went up or down. Let's get a better visualization of this. The model correctly predicted when GameStop highs would go up or down 79.7% of the time. For low prices, the model correctly predicted whether GameStop's price would increase or decrease 82.6% of the time. If we break these graphs apart further, we see that for the high prices of our incorrect predictions, 71% were price decreases that we missed, and 29% were price increases that we missed. Of the correct predictions, decreases were predicted at a slightly higher rate. For the low prices, 83% of the incorrect predictions were increases that we missed, and 60% of the correct predictions were increases in the day's low price. Overall, the model was able to correctly predict whether GameStop's price is going to increase or decrease 81% of the time. This number was surprising to me, considering that the neural network had no information about the stock's price history. It was working purely with Reddit data. It is important to acknowledge that this was a very unique incident. Hedge funds happen to be short squeezing a company that millions of people feel nostalgic for, and they came together in a loosely coordinated effort to save it. However, several other stocks have seen similar but less dramatic behavior. The term meme stock was coined to refer to stocks that quickly skyrocket in value due to social media attention. In future research, I want to explore pulling data from multiple social media sources and pairing that with several unusual stocks or cryptocurrencies to see how they all interact. Thank you all so much.
Thank you, Ben. That was such an interesting thing to watch happen in the news and to learn about. And so it's nice to see you do something with that data that you were able to collect. Next, we have Genevieve Dorrell. And Genevieve will be speaking with us about using remote sensing data and a convolutional neural network to predict wildfire severity.
Hi everyone, I'm Genevieve. So yeah, today I'm presenting on my thesis, and it's about trying to predict wildfire severity so that we know which forests we need to manage. So first, why should we care about learning about wildfires? So wildfires have become a huge danger on the West Coast. So this map here is of all of the wildfires in Oregon since 1984. And while the number of fires isn't actually increasing, the size of them is increasing, and that's what's causing sort of all of this danger, these giant mega fires. And this picture over here on the right is actually a picture I took of my hometown. We had a really devastating wildfire go through my town, and that's why I really wanted to do a thesis that had to do with fires, just because of all the impacts they're having on the West Coast. I'm sure everyone knows about that from the smoke this summer. So why use machine learning to study wildfire severity? Well, it's been done before. You have two options when you're trying to model something like this. You can either do a physical model where you capture all of the physical characteristics, like the exact amount of trees in the area and the temperature and all of that. The reason I didn't do that is I'm not trained in it, but also those models are hard to create because there's a lot of variables in wildfire. So machine learning can be used to sort of estimate it without having to know all of the physical variables that we would need to isolate to accurately predict the severity. Also, we're in the age of data. So there's actually a lot of data on the forests on the West Coast because studying wildfires is a really important area of research. And so the US government has been collecting tons of data sets about that area. So this is a perfect area to implement some machine learning methods for. So what exactly I'm going to try and predict is the severity of pixel by pixel images. So if you look at this map over here, this is from the Monitoring Burn Trends Severity Project, and they have a map for all major fires that happen in the US like this. And it has all of these different classes of pixels. I only predicted these four, so unburned to low, low, moderate to high, and each pixel is a 30 by 30 meter grid. And these pixels are actually, these maps here are based off of a Landsat image of 30 by 30 meter pixels. And they classified each pixel into one of these four severity classes. So this is why it's a great problem for machine learning. You can use a classifying machine learning method to classify all of the pixels in an image. And the goal is to produce predictive fire severity maps that we know which areas of the forest might be safe for wildlife refuge or firefighter refuge and which areas are more in danger of having a very intensive fire that we should manage and look out for. So This is the study site I chose, and the severity maps that I showed before were actually of this study site as well. So how do they calculate those severity maps? They use these before and after Landsat images, and they difference the values in the vegetation pixels, so pixel values, and then they classify the differences into those 4 categories. And so this is the before and after. There are 2 separate severity maps because the areas are a little bit separate, but they started at the same time from lightning ignition strikes. So they're considered the same fire essentially. And I'm studying around 20,000 hectares of forest land in this data set. So now, as of that image before, the only thing I had to train my model on of what the forest looked like before the fire was the Landsat image. I needed to add some other variables so the model had more stuff to learn about. So the other variables I wanted to add were, so the lost year of the forest since 2000. So that means if the forest was cut down since the year 2000, I have data on the year it was cut down, so clear cut. And then I have data on the overall tree coverage in the year 2000. So that should fill in the spaces of forests that didn't lose any forest since the year 2000. So I still have data on it. I have information on the slope, the elevation, and the distance to the closest stream, which is supposed to estimate like the moisture of the area. That's a little hard to do without considering weather, but that's sort of more in my future directions. And the stand age index, which is an ecological indicator of the stand age. So going through those different parts, the first thing I want to show you is this. So this right here is the slope in a TIFF format. And this is what the data set looks like in that area. And then this is the aspect, which is sort of the direction of the slope, which lets the model know whether or not it's a north or south facing area of the mountain range, essentially, which can also help determine moisture. And then this one over here is actually the elevation TIFF that I was using. So the next visual representation of the data I'm using is this one. So this is the lost year. And as you can see, like I was saying, there's a lot of black areas where we don't have any data. And this TIFF over here of the forest coverage in the year 2000 is supposed to fill in those data pieces to let my model know the general forest coverage of the region. And then the distance to stream. So this is also from the US Forest Service. It's a generated stream location ArcGIS file of all the streamlines, and I used ArcGIS to calculate Euclidean distance of every single pixel from the stream and use my model to train it on that value. And then lastly, this is a stand age index. So this is essentially a bunch of ecological factors that are added together to estimate the stand age index. The value isn't the actual age of the trees. It's ecological factors that are good indicators of a stand age index. And these are trees that fit the sort of schema of being at least 80 years old. And then these ones are ones that fit the schema of being like 200 years old. As you can see, there's this checkerboard pattern that has to do with building the railroad and who got land and timber rotations. If you've ever studied forests, I'm sure you've seen the checkerboard pattern in forests before. So how did I organize my data set? I organized my data set by using the surrounding pixels as part of my data. So if you look at this figure over here, the center pixel is a pixel I'm trying to predict the severity for using all of those different descriptive factors, but I also actually included the values of these pixels and these surrounding pixels as well, because the surrounding pixels do influence the severity of the central one, and it gives the machine more data to train on, essentially. So overall, my data set had 82,000 data points. And then I had a separate test data set, which is 2,000, and it has 500 randomly selected data points per class. So that means 500 low severity data points that were randomly selected, and high and moderate. So, and then I calculated the descriptive factors that weren't the Landsat image using the longitude and latitude of the center of the pixel. So that's how I determined which distance to the stream to use or which stand age index value to use. So knowing that, we're ready to start to start getting into some of the machine learning model stuff. So I evaluated my model using loss and accuracy. So I used the cross entropy loss function for all of my neural networks. And then for all the models that didn't have a loss function and all of those as well, I used accuracy. The main predictor you'll see is I'll say how accurate the models were at predicting my test data set that the model did not train on. So those 2000 data points that I held back and didn't train the model on. So first, here's some classic machine learning methods that I used. So I ran the data through a logistic regression and I got an accuracy of 44.6, which is the randomly choosing the data points. I would get an accuracy of 25% because there's 4 classes. So it's better than random, but not much. The decision tree is a little bit better, but not particularly great. And then the random forest, one of the last classic machine learning methods I tried, was actually pretty accurate as far as ecology stuff goes. So that was a bit of a surprise, actually. I was not expecting it to be that good. So because of that, I did create an error matrix for the random forest. And so the random forest model was best at predicting low to unburned area. So an error matrix sort of tells you what other classes a model is predicting a pixel when it predicts it incorrectly. So you can see if we're looking at the random forest classification of the unburned to low pixels, it gets most of them right as being classified as unburned to low, but if it gets it incorrect, it's more likely to do low and then moderate and then high, which is good because you would want it to be more likely to predict a severity that is closer to the one that it actually is. And as you can see, that happens for all of them. So usually the highest missed data class is the one right next to the severity that you would expect. And then the ones highlighted in green are the percent correct, essentially, for the different severities. So the average I showed before was an average of these 4 different correct predictions. So the random forest, we weren't really expecting it to do that well, but it did do pretty well. And then the next model that I really spent some time with was the deep neural network. So this is just a deep multi-layer feed-forward perceptron model. And I used the ReLU function to introduce nonlinearity and a soft max on the last layer. So this type of model is inspired by the human brain. And each of these nodes is essentially supposed to be a neuron. And they each hold individual weights, and the weights at these nodes is how the model learns data and then actually remembers the data. So you can use that neural network, save it, and then use it to predict on new data sets, essentially. So how well did my deep neural network do? It got an accuracy of 64.85, which is actually less than the random forest. But we have one more model coming, so not too sad. So it did the best with class 3, and that is kind of exciting because we do want to know what the highest severity areas are, because those are the areas that we need to watch out for in wildfires. So that was kind of exciting. And this model actually did the best at predicting the high severity by a good amount. And if you look at the loss and accuracy graphs over here of over the epochs, you'll see that there is a little bit of overfitting, meaning that the model more accurately predicts the training data set versus the test data set, but not very much. So these loss and accuracy graphs look pretty good for a neural network. Now here's the error matrix for the linear neural network. And as you can see, the 75 is good. You can also see that it's more likely to predict higher severities instead of lower severities. So if you look at at all of the rows, the model is more likely, if it's trying to classify an unburned to low pixel, it's more likely to classify it as a higher severity, which is useful because you don't want a model to underpredict the severity when it should be predicting a higher one. And again, it's pretty exciting that it was able to predict the high severity so accurately. And then The next neural network that I tried to create was a convolutional neural network. It was a 1D convolutional neural network. And I used the ReLU as my activation function again, the softmax as my output function, and max pool in between each convolutional layer. So how did this model do? This model is the most accurate by a little bit, and it does pretty good again at classifying the lowest severity, which again is useful. Highest and lowest severities are the most useful because you can either determine that that would be a good area to try and protect as like an ecological safe haven. But if you look at the accuracy and loss graphs, you can see that there is a bit of overfitting. So if you look at the accuracy, it's a lot more accurate on the training data versus the validation data. So that's the test data that was held out. So the model is a little bit over complex maybe for the problem. Here's the error matrix. Again, it is actually more likely, well, in most cases, it's more likely to overpredict the severity. But again, it's more likely to predict the severity that is closer to its actual severity. So if it's unburned to low severity, it's more likely to predict a low severity instead of a high severity for that pixel. So again, that's some good news. So in conclusion, this is sort of a problem that people haven't really tried to apply machine learning to very much. So it's exciting to have some results on that. The neural networks in RF random forest perform the best, which is pretty cool. Some of the issues is that the current model is very region specific and it's very climate specific. So those fires burned on the same day or the same set of days. So I don't have any variation in climate data. It would be really interesting to add weather variables in for future directions. One thing that is also exciting is all of the data sets I used are available for all areas up and down the West Coast. So this could be applied to other geographic areas to produce fire severity maps in those areas as well. The current literature on this has a random forest that has like 31% accuracy. So this is definitely cool in that it adds some new stuff to the literature. And then overall, these are the accuracies again. And thank you guys for listening.
Wow, thank you, Genevieve. That was great. Up next, we have Myles Nelson with predicting the metabolic cost of level ground walking from gait speed and prosthesis stiffness.
Awesome, thank you. I'll get going and share my screen here. All right, here we go. So yeah, hi everyone, I'm Myles Nelson. I'm a human physiology major. I'll be graduating in 2 weeks, which is awesome, but I'll be talking about my thesis today. So each year, the number of individuals requiring the use of a prosthetic limb continues to rise, as there are over 150,000 lower limb amputations per year in the United States. And so the use of a prosthesis is supposed to help improve health and mobility. However, quality of life remains lower compared to those with intact limbs. And so some of the limitations associated with the decrease in quality of life are decreased balance and lower mobility than those with intact limbs. And as a result, those with lower limb amputations walk at a speed that's anywhere from 7 to 42% slower than the able-bodied individual. And so many of these users walk at these slower speeds in an attempt to lower their metabolic cost. And metabolic cost refers to the energy expended or used by the human body during ambulation. So on average, prosthesis users with lower limb amputations expend about 16% more energy. And this energy expenditure depends on several factors, such as the amputation level. And these prosthesis users are walking at these slower speeds in an attempt to lower their metabolic expenditure back to that of an able-bodied individual. However, because they're walking at slower speeds, it takes them a longer time to walk the same distance. And so the overall metabolic expenditure still increases. And so one reason for the increased metabolic expenditure is the difference between current prostheses, which use a single stiffness, while the biological foot-ankle complex modulates its stiffness with every step. And so as a result, previous literature shows stiffness is associated with comfort and energy expenditure during gait. However, the previous studies show that there are mixed results when it comes to stiffness settings, whether it's low, medium, high, or at all, to which best reduces the metabolic cost of walking. And due to the lack of concrete evidence around the importance of prosthesis stiffness, I conducted this project to answer the question, how do prosthesis stiffness settings and gait speed affect the energy required to walk, which I would answer using a regression model. So I hypothesized that the regression curve would have a three-dimensional parabolic relationship with the local minimum near the intersection of the median stiffness and velocity settings. Additionally, I hypothesized that the velocity-dependent portion of the regression model would be improved by stiffness alterations. So let's look at the protocol I ran in order to find these effects. It was a 5x4 block, which consisted of 5 stiffness settings and 4 speeds. And each trial was a single stiffness setting with a randomized order of speeds that the subjects went through. Each of these trials lasted about 12 minutes, which allowed time for subjects to reach metabolic steady state at each speed. And so if we look here at image A, this is an experimental setup for the participants. They used a walking boot, which you would typically use if you broke your foot, which had the prosthesis attached to that. There was then a lift shoe to allow for same height difference because there was added height with the simulator boot, as well as a metabolic mask, as I recorded metabolics via a collection of inspired oxygen and expired carbon dioxide. And I also recorded the heart rate via a chest monitor. And the last 30 seconds of each speed were taken and processed in Excel, as well as in MATLAB using a custom script I wrote over the summer. From there, I used data analysis in the SPSS software, which included making the regression model, as well as a multifactorial repeated measures ANOVA to analyze any within trial differences. So what makes my project different than previous studies is the use of the variable stiffness foot prosthesis, which is shown here in image B. This was designed at the University of Wisconsin-Madison by Peter Adamczyk and his group there. This prototype allows us to use one prosthesis device for all stiffness settings, which limited many confounding variables within my study. This prosthesis contrasts that of the popular energy and storage return prostheses, as those ESRs use a spring to store and return energy to their users, but often at one stiffness setting. Whereas the VSF acts more like the biological foot-ankle complex because of its ability to change its stiffness due to the use of an actuated keel, shown here in the black, with a movable fulcrum, which is here, to allow for modulation of the forefoot stiffness. It works similar to that of a diving board you would see at a pool. So if we look at this table C, which tracks the effects of stiffness and gait speed on metabolic expenditure, in my study, all participants demonstrated an increase in metabolic expenditure as gait speed increased. And this is true at all stiffness settings, as you see when you look across the row. So if, for example, at the 15.3, we start at 11.9 at the slowest gait speed and go up to 18.6 at the fastest gait speed. And there was a main effect of gait speed with a p-value of less than 0.001. And the ANOVA revealed several between trial differences, which I showed using symbols here to denote the pairs and their significant difference. However, if we take a closer look at image D, we see an easier depiction of the increase in metabolic expenditure due to gait speed. And this linear pattern we see here is a pattern found throughout the literature. Studies by Sims et al. And Wei et al. Had parabolic curves. However, they used much wider ranges of walking speeds. So if we were to zoom in on the speeds I used, which was 0.8 to 1.4, in those studies, you would also see this more linear curve rather than the curve of a parabola. So in contrast to gait speed, there is no main effect of prosthesis stiffness settings on metabolic expenditure, which is shown here in image E with the pretty flat lines here. Qualitatively, this graph depicts that at 3 of 4 speeds, there was an increase in metabolic expenditure between stiffness settings 2 and 3, which was the 18.6 and 23.6, which is shown in the purple, blue, and green lines. However, this was offset with a decrease at the firmest stiffness setting at 2 of the 4 speeds, shown in blue as well as yellow. These results don't match my hypothesis, as we thought stiffness would play a greater role However, it does depict that ambiguity in research. Like I stated previously, many studies found that either low, intermediate, or high stiffness settings were best to reduce the metabolic cost. And while previous research already shows the similar ambiguity around the effect of stiffness, my project adds to this literature due to the use of the VSF, which allowed for a twofold change in the stiffness settings without swapping devices, unlike other studies which had to use several running blades or dual spring mechanism prostheses. So now let's look at the multivariate regression model, which was a generalized linear model on SPSS. The model had a R² value of 0.842 with a root mean squared error of 1.088. However, that's kind of hard to understand, so I normalized that, which gave an error of 7%. The beta values for the regression model were 0.9 for gait speed and 0.13 for prosthesis stiffness. And so the closer that number is to 1, the more importance it has within the regression model. If we look at image F, the metabolic expenditure measured in my trials were on the y-axis, plotted against the predicted values from the regression model on the x-axis. And you can see the strong linear relationship denoting the 0.8 R² value with very low variance, which goes towards our 7% error. I believe it didn't follow the three-dimensional curve that I mentioned earlier because of the lack of effect by prosthesis stiffness. And so it followed the more linear version that we see here in image D, which has to do with the gait speed. And so I believe a larger velocity and threefold stiffness change may have led to more of the parabolic shape that I was looking at, which is seen in previous literature with larger ranges. So because of the lack of effect on metabolic expenditure by prosthesis stiffness, I decided to take a closer look at specific subjects. So the reason why I chose to do this is because previous literature has shown that prosthesis stiffness settings, gait characteristics, and subject perception are really important factors for the optimization of prosthesis fit. And so in my study, the overall effect of gait speed was very similar between the two subjects, which are denoted as subject A and subject B, as seen here in image G. There are several differences at specific speeds, which we can see here. At the lower range, which denotes the 0.8 speed, it was very flatline for subject A, while we have a large peak at the middle stiffness setting for subject B. However, if we look at the largest velocity at 1.4 meters per second, there's a large depression and then a large jump for subject A, while it's very flat for subject B. But there are more quantitative differences in metabolic expenditure due to prosthesis stiffness. If we look here at subject A, at 23.6 Newton per millimeters, there's a large trough, where at 28.6, there's a large crest. However, it's quite opposite on subject B with a large crest at 23.6 and a large trough at 28.6 Newtons per millimeter. And I believe there are several reasons for this. One is due to subject specificity and how they perceive the level of effort based on stiffness and gait speed. Subject B often depicted that the middle stiffness setting was hardest, and this makes sense as we see the crest at the 23.6 setting. In addition, user satisfaction with fit is very important, and subject B struggled with the fit of the boot throughout the collection. And research shows that the better the fit, the better the satisfaction, as well as performance in regards to metabolic expenditure. And finally, the subject's adaptation to walking with the boot is very important. Subject A tended to load the lateral aspect, which caused increased torque while walking, which could have been exacerbated by higher stiffness settings due to low compliance, which led to their 15.3 Newton per millimeter, shown here on the far left, being on average their optimal setting. So in conclusion, to summarize the findings we saw, the effect of gait speed affected metabolic expenditure more than prosthesis stiffness. The ambiguity around the effect of prosthesis stiffness shows the importance of subject specificity, which was further proved by my study. The regression model followed a linear relationship rather than a parabolic due to the lack of stiffness setting, and so it often followed the gait speed settings. And subject specificity, subject adaptation, and user satisfaction are crucial in an individual's performance when it comes to walking on a lower limb amputation prosthesis. So this research could really be used and best applied during the fitting process, as it could aid in the detection of minute changes in prosthesis stiffness and better optimize the prosthesis for its user. However, in all honesty, I have to say, before this could be used clinically, there needs to be further research done. First, the ranges in my study don't depict the ranges used in someone's daily activities, whether it's walking speed or different stiffnesses. So it would be best to use larger ranges for both of those to better understand their effect on exertion during walking. Second, it would be best if the prosthesis made real-time stiffness adjustments to better mimic this biological foot ankle complex. And for this to happen, not only would the VSF need to use accelerometer data, which it can already do with onboard IMUs, but we would need to explore the realm of machine learning so that the prosthesis can become optimized to its user. This could lead to precise stiffness changes based on the user's specific gait characteristics, which would help us minimize metabolic expenditure for each different subject. Finally, I'd like to thank the UO Cure office, as well as the Clark Honors College for funding this project, as well as all of the members of my team and lab for helping me do this. Thank you.
Thank you so much, Myles. I'm very impressed with all of you and how much work you've been able to do during a really tough year. So we're going to go into the Q&A portion now. And before we do that, I want to thank Jackie Etchison for tech support during this session. And I also forgot to introduce myself. I'm Bronwen Maxson. I'm the coordinator for undergraduate engagement and instructional services, as well as the subject specialist for Spanish, Portuguese, and Latin American studies at UO Libraries. We have a question in the Q&A from Noah for Genevieve. Genevieve, I'll read it out loud and feel free to respond. You can unmute, yeah. So Noah asks, how can random forests be used to determine what features have the most predictive power?
Yeah, could I share screen real quick? I have a slide
Please
for
do.
this.
Yeah.
Where is it? So yeah, it's actually the next slide. So this is some preliminary stuff that I didn't quite show because I don't have error bars on it yet. But random forests are cool because when you're using machine learning, you can't determine what features are predicting the severity the best. But random forests, it's easier to do that. So I have some cool data telling me which of the features that I included are predicting the data the best. So right now, for some reason, it seems to be elevation, which is cool. So technically I have like 425 features because I have 25 pixels for each data point. But so this is the average for each of these different features per pixel. So yeah, no, it's interesting. I'll be able to say some stuff about what I included in my data set that's helping me predict fire severity. So yeah, no, thanks, Noah.
I don't see any other questions in the Q&A, but if anyone watching wants to ask a question, go ahead and put it in there. Meanwhile, presenters, you're welcome to ask each other questions. And apologies for the chewing dog in the background. Go ahead, Genevieve.
Ben, did you try your model on anything besides the GameStop stock?
I haven't run it on anything else yet. I have it set up, the infrastructure set up so that I can pretty easily, and I do plan on doing that. I just haven't yet, but I think it'll be super interesting. I'm not sure it'll work as well because I think it was really dependent on the fact that Wall Street Bets had, thousands of posts every day talking about GameStop. And so when you don't have the same sort of activity going on, it probably won't be able to predict for other stocks as well. But there are other stocks that they're talking about that would be really interesting to look at.
Thanks. I'm curious to hear from each of you how you got interested in your topic in the first place. Maybe we can do Ben, Genevieve, then Myles.
Yeah, sure. I mean, I've always kind of followed the stock market and economics. And I look at Wall Street bets. I've looked at Wall Street bets for a couple of years now. And so when they started like actually having a big impact on the economy, I thought that was super crazy and interesting, because it was just this little tiny group on a random part of the internet where people gamble basically. And I thought it was entertaining. And then it started having like huge economic impacts, like tens of billions of dollars at least. So that's where my interest came from. And I'm really happy I did the project. It was super interesting.
I guess my interest sort of came from reading the literature. I wanted to do a senior thesis because I had the time, and I wanted to combine my two majors, biology and computer science, somehow, which is kind of hard to do sometimes. So I was talking to one of my advisors, Lucas, and he was like, you could look into wildfires. And I just felt really passionate about that because of what happened in my valley. I lived in Ashland, Southern Oregon, and they got really burned last summer, and I wanted to do something to help, I don't know, try and make that not happen again. So yeah.
That was, oh, go ahead, sorry. I was gonna say that you had mentioned your hometown, but you hadn't named it, not that you have to name it, but my parents live in Black Forest, Colorado, and there was a massive Black Forest fire in 2013, right after the Waldo Canyon fire in Colorado Springs in 2012. So I'm with you on that.
Yeah, no, they're pretty devastating for sure. So yeah, I wanted to do something because I felt like I cared about that enough. And I'm really glad I did this project. It turned out really cool. We might publish it because, like I said, there's not stuff about it. So that's pretty exciting. So yeah.
Very exciting.
Also, hi, Sam.
So I became interested in my project. So I've been in the lab that I've worked with, which is the Bowerman Sports Science Clinic. It's a human physiology lab here on campus. I started 3 years ago and initially looked at ACL injuries and how to prevent that in specifically soccer players. But I had the opportunity in my sophomore and junior year to create a 3D printed prosthetic arm for a local middle school boy. And we were able to actually print that and give that to him. And it was an awesome experience. And that really started me down the path of prosthesis and those devices. And luckily, one of the PhD students in my lab was also studying this foot. And so I was able to kind of hop on and create my own trail off of it and start this project to really look and see if we can predict the best settings to help those users, have the best lives they can with the prosthetics they're using.
Great, thank you. And I've got Clara in the background entertaining us. Do you have any other questions for each other?
What are your guys' majors? Just out of curiosity.
I'm a computer science major and math minor.
I'm a human physiology major with minors in chemistry and Spanish.
And then you mentioned your biology and computer science, Genevieve. That's a really interesting combination. I think it's really cool. What kind of stuff do you want to go into when you're trying to find a job? Like, are you going to try to combine them or focus more on one or the other?
I am graduating, so I got to figure that out. I'm not entirely sure yet. I'm going to use my computer science major for a bit, I think, after I graduate, and then I might just go back to grad school because it's hard to combine those two majors unless you're doing research.
And what about you, Myles? What are your aspirations?
Yeah, so I actually submitted my first round of medical school applications this morning. I'm looking to go into medicine. I think my work with prostheses has really kind of tailored me more towards maybe orthopedics and things like that. But I also have seen the need in underserved communities, especially rural communities. And so I think maybe working in that area would also be really cool. But how about you, Ben?
That's awesome, man. Yeah, I'm not totally sure yet. I'm a sophomore, so I'm not very far into the computer science program yet. I want to do some sort of software engineering. I think cybersecurity is super cool. I think machine learning is super cool, but I'm just not totally sure yet.
Wow, you're a very impressive bunch. Thank you so much. If there are no other questions, we can stop recording. I'll just give you a few more moments if there's anything else.
No comments or no questions rather, but just wanted to say great job, everyone. All of these projects take an inordinate amount of work, and I'm super impressed by the quality of our undergraduate research projects. They always astonish me every year how what great quality comes out of it. So thank you guys for putting in the hard work and making it success.
Would you like to also introduce yourself since you're?
Yes, I'm Sam. I'm a PhD student here at the University of Oregon. I worked a little bit with Ben. Ben did all the heavy lifting, and I just gave him some pointers here and there. But I've also worked with Genevieve in the computer science context, and she's always been a pleasure to work with. And I don't know Myles, but I wish him well as he goes off to medical school. So
yes, good luck. Good luck to you as well, Genevieve, as you job hunt, and Ben, good luck as you kind of figure out your path through your major. Very cool. Well, thank you very much, everyone. I will stop the recording, and I hope you have a lovely rest of your day.
Thank you, guys. Yeah, great listening to your presentations.